Thank you very much. So it's on now. So I don't know whether I managed to stay here all the time, so you may hear me better or not so good if I move or not, but I do my best. I changed the title a little bit. So in the program you found characterization and microscopy of nitrides. I changed it toward the purpose, actually, and said, okay, we're not doing characterization just for fun, and okay, it's fun, but we don't do it just for nothing. We do it because we want to know something about the electronic device afterwards and about the materials inside the electronic device. And this is what I want to deliver to you. So the talk is not just many things of characterization, how you put a crystal or an epi layer or something in some characterization device and achieve some data. This is not what it's about. So what I want to deliver to you is more kind of a mindset, kind of a way how to achieve knowledge about how things go together. So you have heard about devices, you have heard from Karen about epitaxy, you have heard from the colleagues from Poland about the crystal growth. And now if we start with crystal growth and then we go ahead, you have to bring everything together. So this is what we are doing at Fraunhofer IISB. So we are actually researching along the whole fabrication chain or value chain until the systems and really the application of that devices. And we start in particular from the crystal growth. So I'm originally a crystal grower. So I learned crystallography and material science and semiconductor physics and all these kind of things. And now the question is whether you just do it for knowing even more and more and more about a crystal structure and how the potential landscape in a crystal is supposed to be, or whether you want to bring it to an application. And if you want to bring it to an application, you have to bridge, in fact, this whole chain from the very beginning, which is the crystal, to the very end, which is something that you keep in your hand or that it's built in your car or something. And this distance is quite huge. So the planet that you have to observe with the characterization to bring these endpoints together to make a knot, this is difficult, this is sophisticated, and this is what I would like to deliver to you today, just to get an idea how to bring things together and how one can do this in a correlative way, and what you have to be aware of if you go into these challenges. So you have heard many times that the gallium nitride and the aluminum nitride, so also I fancy the aluminum nitride as a new kind of semiconductor very much, are probably the most important materials that we're working on nowadays. So let's say after silicon times, these two classes or these two nitrides are maybe the most important class of new semiconductors. But before you have anything in your hand, like a device or an epitaxial layer or something, you have to deal about the crystal. So the crystal really is the key material. And this is what you heard in the lecture by Majoszka yesterday. So this making the crystals is an essential problem itself. And all you start here, you will see until the end to the value chain. So all the errors that appear when growing the crystal, all the defects that appear in a non-perfect material, then this will go on and on and on and on until the end of the end performance of that device. And this is why we have to watch the whole value chain at some point. And it's quite complicated, so be aware that you hear a lot. And let me know if you have questions, so it may be also fast. And I do my best that you don't fall asleep after meal. So as I said, we have to bring a lot of things together. So at one end you have the device. And this picture now here stops at the device properties. So after the device properties, as you have seen before, there are the systems. So you also have to bring these chips that you finally make. You have to bring to some system, to a car or to a converter, to an inverter, to whatever industrial motor drives, whatever you do with this. But they should have some certain performance, which is a minimum performance above something that you already have now if you want to implement a new material. And it starts with something like the process in crystallography or in crystal growth or in epitaxy. At the very left side you see an epitaxial reactor. You can look inside that and you see that there are parameters like mass fluxes, you have heater power, you have temperatures and all these kind of things, and you have to finally link together the process parameters with the properties of the material that you're producing, whether it's a crystal or an epitaxial layer, and finally to the performance of the device. And this is quite a way to go. So you have to look also on very different scales. So things go on an atomic scale. So you have something like a dislocation or an arrangement of atoms, which is on an atomic scale really. Then you have something that is larger, you have a machine. So you have mass fluxes, heat fluxes, temperature, which is on the order of the size of an HVPE reactor, which is taller than the room here. Or a silicon Trochatsky puller, which is 3 floors tall. And on the other hand, you have something like, which is a sort of a device. So you have some millimeter times millimeter, or micrometer times micrometer, or layer thicknesses in epitaxy, which are on the order of micrometers. So all these different scales you have to observe and bind finally all these things in terms of process parameters, fabrication parameters, materials properties, and later performance to one another. And this is quite a big scene that you have to observe and to address. I think you have heard this many times before now. We say that the nitrides have a high potential. And here, just to show this, on the left side, you see where the aluminum nitride comes into play. There would be also the region general for the ultra-wide band gaps materials. So you also have the gallium oxide in that region. You also have the diamond in that region. So I would say the aluminum nitride and the diamond comes into laying at more or less the same place. So this is a good justification why we look also on these materials. So in the talk you will hear from both materials, gallium nitride and aluminum nitride. And this is, I'm not going to repeat because Farid explained it very well, that there is a good justification because you can also achieve higher efficiency. And if you really look into the situation that we also have nowadays, efficiency also in terms of thinking about how much energy and we can save for the benefit of the climate, this is also very important. And also the data centers get larger and larger, and the amount of data that we are really handling is getting so huge. So it's not only about automation, about industrial drivers, about power switching. So it's really also about applications in let's say surroundings, industrial surroundings, where efficiency is the highest good. This I skip because we know this already. So how can we do this? What have we to make, or what do we have to consider if we want to bind all these things together from the different sides coming into play? Then you just have to keep in mind what is in the heart of a semiconductor device. So a semiconductor device, if you strip everything off, it's simply spoken a sequence of epitaxial layers that are deposited on some substrate. And the functionality comes from semiconductor physics. So in case of the nitrides, you have some polarization fields and you create a 2-deck. What Farid said, you get it for free, so you don't need any doping. In other types of devices, you need some doping. But this is really simply what is inside a chip. So just a number of layers. And then the technology comes into play. Technology means everything you do after you have deposited the device layers, the functional layers. So you have to structure it, you have to do some etching, you have to do deposition of metals and all these kind of things. You have to clean surfaces, you have to deal with interfaces. All these things finally make the device. But from a materials point of perspective, it's only the sequence of the layers that we're looking at. So, and this is something from Henry Petrosky, and Henry Petrosky is not a semiconductor physics. Henry Petrosky is an architect. So he builds houses, buildings, he's a builder. But he said, and this is very true in general, I would say, successful engineering, and we've considered this in successful engineering of electronic devices, is something where you have to understand how things break or fail. And if you know how things break or fail, then you can go back and say, okay, now I know what I have to do better. It's always the perspective from the backside. So if you cross the bridge, you say, okay, now I know how the bridge looks. Very easy. Of course, it's not so easy because we also have to do this with a future perspective, looking forward. But on the other hand, we have to learn about the things that are existing and why they do what they do and how they function. What does it really mean to us? We must learn how devices function, physically, really. How does dislocation maybe affect something or an interface? So how does it really function physically? We have to understand what compromises then the functionality from materials point of view. And after we have understood that, try to create the holistic picture. Try to understand everything from processing the material to the final system or device. Then we have the full picture. Of course, this is something which is huge. So not a single scientist will manage to create this holistic picture. So this is, I would say, a cumulative action. So this is a common action. So many people should work on this. If we put everything all together, then we manage to create the holistic picture. So how can we achieve that? I would say characterize. Characterize what you can, but do it with a good purpose and a clear target, with clear questions. What do you want to solve? But only what you can see, you can change. So only if you have measured something, you can understand something. Only if you see a dislocation at a certain place, maybe underneath a gate, you can understand, okay, I've seen it, it's a clear evidence. But be careful not to be cheated, it's not so easy. This is what I want you to bring through, and where I want to deliver to you, let's say more a global point of view, a global, a bird's kind of view, looking on the things and say, okay, I have to do this and that in order to understand the whole picture. I order it along, let's say, a manufacturing flow. This is a picture that you will see sometimes again and again, which says, first of all, understand the crystal. Understand how a crystal grows and what can be grown into a crystal, and then you can understand how this is carried forward over the whole processing chain. We will deal with some substrate issues. I will show you some issues to the epitaxy and the devices, and then we deal shortly with some properties of dislocations, and I will show you what are the consequences of the crystal in the real structures for epitaxy. And then we will talk about how we now can learn how dislocations are relevant to the electronic devices. And you see, it's 3 points, and what we consider is the most relevant to understand why an electronic device, a transistor, functions like it is and why it fails. This is the last point. So you have to work through all the other things first and understand it, and then you say, now I get the clue. I put it just in boxes, saying, okay, you have a raw material. We have to make some seed. This is prior to crystal growth. Then we put the seed and we grow a crystal. I think this is something that you have seen from YESvGaN yesterday, the gallium nitride crystal growth. You all have to talk about the seed. This will determine also how good the crystal will be. So there is also something before the crystal. So it's an endless chain before and before and before. We start with the crystal growth. Then we have to make wafers out of this. Of course, crystals, you have to process the ingot, you will see later, and then we go along the chain, and at the end is the processing of the device. It's at least 3 stations, I would say, 3 stops. If you put always 3 boxes together, the 3 left ones, the 3 middle ones, and the 3 right ones, you have 3 stations to go. So let's talk about the crystals first. What is a crystal? A crystal is a big piece of semiconductor. But creating the big piece means something, and what is inside the crystal such that it functions as a semiconductor. So if you look from an atomic point of view to a semiconductor, it is an arrangement, a strict geometric arrangement, infinite, with the most perfect arrangement of atoms. So it should not have, by definition, any defects. This is a perfect crystal. And it should be like this because we're talking about semiconductors. So a semiconductor is from an energetic point of view seen just a a potential landscape. So you had atoms creating a potential, then you have no potential in between. Maybe you have doping atoms creating a potential, missing atoms, but this is all the real crystal. So the perfect crystal by definition has no defects. So it's a perfect lattice, periodic and infinite. But now we have some defects in the crystal because nothing is perfect on Earth. And we're talking about a real crystal. So how does a real crystal is being formed? So the fundamental of crystal growth is, if you want to have this perfect lattice, you have to order this big solid body atom by atom by atom over a process with process conditions that you can steer, like temperature, furniture power, gas flows. So these are very rough parameters. Imagine you have very rough parameters, turning a knob and your gas flows faster or not so fast. But what you're doing in fact is piece by piece, atom by atom, ordering a perfect lattice. So this is a big challenge. And then you have to see, okay, can I make the material, can I make gallium nitride and aluminum nitride in this way, and how shall I do it? So can I melt it? This is very easy. This is done by silicon. So you have a raw material, you maybe melt it, or you solve it, or you evaporate it. But this depends on the material, whether you can do it or not. So first of all, you mobilize some building blocks, and then you condense and order the perfect crystal. Now you have to find what is the best growth method. And finding the best growth method, or the most fitting growth method to the material that you have, also means that you may be able, better or less good, to achieve the most perfect lattice. If you choose the wrong method, for example, which doesn't fit well to the material, you end up maybe with a material that has more defects, rather than if you choose to have a growth method that fits very well to the material and the material properties, and you end up with a more perfect crystal. And at the end, this counts for epitaxy. So if you have a material that you can melt, it's very easy. There are many examples of this, but this is not the case for the nitrides. So the nitrides come into play if we talk about materials that can only be evaporated and not melted. Then you have the aluminum nitride, for example, by the physical vapor transport, so PVT processes like silicon carbide, and the HVPE process, which is a chemical mediated gas phase process for the gallium nitride. And if you do some solution growth, you can do this if the material is not meltable and if you cannot sensibly evaporate it. And this is where the high pressure solution growth, the sodium flux method, the monothermal growth for the gallium nitride comes into play. And those are all comparatively difficult methods compared to classical crystal growth of a semiconductor like gallium arsenide or silicon. So this is much more difficult. So from a crystal grower's point of view, we say, okay, the nitrides really put a big challenge to the crystal growers. And this also means that it's even harder to grow the crystals larger and thicker, such that you achieve more efficiently more wafers out of a crystal. So keep this in mind. And then we say, okay, a single crystal. Now we need to characterize the crystals. So this is the starting point. How good will be the epitaxial layer if we regard the perfection of the crystal? Because the crystal perfection will be a fingerprint that is being taken over to the epitaxy. So we have, let's say, single crystals, bulk crystals, volume crystals are all the same. Bools is sometimes a name for it. So this considers a large individuum, a big piece of a semiconductor with one lattice all over this big piece. Then we have crystalline layers, which can be polycrystalline with strong preferred orientation, I would say. Or we have a very large but very, very thin one individuum, which is an epitaxial layer. All these we have to consider because this is all important for the final device. So how do we characterize the volume crystal? This is what we do first of all. So we have a crystal which is grown, we take it out of the machine. This is an example for aluminum nitride crystal. And aluminum nitride we have quite a lot of chances to analyze, but you can imagine that it's not so easy if you have a big crystal. So if you have a big crystal, which is such a piece, or even aluminum nitride or gallium nitride, which is a smaller piece, the gallium, for example, is a very huge absorber physically. So you cannot just shine with an electron beam, or just not shine with an X-ray beam through the material, because it's such a strong absorber, you will see nothing. So we go to other methods which are more sophisticated, which is, for example, a high energy transmission, Laue diffraction, which operates at 480 kV molybdenum tube. And what we can do then is we have a so-called defocused and focused mode, and we can shine through the crystal, and on one hand we see something which is like a rocking curve. So we see, even at the beginning of the crystal, we can analyze whether this crystal is good or not. It means that we may do the effort to slice it, or we just trash it. And we have the direct feedback whether the crystal growth process was good enough or not. So we say, okay, now we see that this crystal process, where we maybe in the growth process changed something like the temperature or so, or whatever, the temperature isotherms, was not good enough, because the result was a real crystal with a lot of dislocations, or with a lot of defects. Which you can see here, for example. Do you see this colorful map? This is a map of, let's say, in the defocus mode, where we see the rocking curves. So we see this is a heat map of the full width half max in arc seconds over the whole crystal. And it's a sum through the whole crystal. So the thickness of the whole crystal is summed up here, the total volume. And we see that there are places where we have less good quality. So we say full width half max, if it's larger, it's less good quality, it contains more, it's roughly spoken, it contains more dislocations than a small value. It's not completely true, but first of all, you can consider it like this. So everywhere where you see blue areas, for example, the crystal is better compared to the places where you see the red areas. Now you want to know what is there at those places. And we say we take a picture now, which is a topograph, which is it's not a wide beam topography, but it's a monochromatic topography in that case, where we see now we can map the structural quality of the whole crystal. And this is what you see, where we then also can mark some areas and investigate closer what had happened in such areas. Now if you want to make a crystal larger, for example, you see at the left side, left lower side, you see that there was expansion to the side here. I would need a pointer. Can you hear me? Yes. So you see here, this is where the arrow is, that we have expanded the crystal by that. And this is, of course, what the ones who make the application with the devices, they want, okay, something like 100 millimeters, so 4-inch diameter, or 6-inch diameter, or 8-inch diameter. Then they say, okay, if you want the aluminum nitride to be the next material, then grow a crystal which is even larger. And you see that you have to deal with these defects, because any of those contrasts is a defect. So you see this crystal, which is on the order of, maybe this is 30 millimeter in size, and you see, okay, there are defects here, many, there are defects here. They should all be not there if you want to make a device. If a device would be on such a place, then it's trash. If epitaxy, which comes on such a place, would be trash. Device on the epitaxy would be trash. So it's one after another. So the crystal, first of all, has to be perfect as possible. And with these techniques, we mirror the quality really of the volume crystal. But now we know where the defects are, and we have to know what it is, because we heard also before in the talk that the type of dislocations may matter. So it may matter more or less what type of dislocations really you have in the device, what they are, or in the epi layer and first in the crystal, which may then tell you whether it's really deleterious for the device or not. And something like, if we do something like defect selective etching, you can see that, for example, if you etch the surface of the crystal by a wet chemical etch, for the nitrides, for example, this is a KOH, NaOH melt under high temperature, under 400 degrees C. Then you see that at any place where there is a location, where there's dislocation, you see in the transmission electron microscopy picture, you see this shape of the etch pit, and underneath you can then see by the G.B criteria, you can investigate what type of dislocation is underneath such an etch pit. Then you make a large area and you count all such edge pits, and you classify them by size, and then you know what type of dislocation is by calibration, you know what type of dislocation is underneath such. It's better? Thank you. I'm sorry, I have to run.
Yeah.
And then you see really what type of dislocation is where, and you can make statistic over your crystal. You say, okay, the whole area of the crystal that I investigate now, if you would go back and imagine the picture from before here, then you see, okay, now if we etch such a slice, we see that there will be many etch pits, and we see, okay, this is a different type of dislocation than that, and this and that. We can investigate such types of dislocation, and we know, okay, they are basal plane dislocations, so they may not appear to the surface, so may not play a role in epitaxy. But such ones that emerge to the surface, they play a role in epitaxy. So this is why we investigate the volume crystals so closely and characterize them in order to know what we have in the crystal and what is really relevant. Now you have something which is also important, which is residual strain. So fundamentally spoken, the crystal during the growth gets strained. So if it gets strained, it may break on an atomic scale, which forms a dislocation, or not. So you have elastic or plastic deformation. A dislocation is nothing else than a plastic deformation to the crystal material that appears, and as long as you have elastic dislocation, elastic deformation, you have no dislocation, but the crystal will be heavily strained. This is also something that you don't want, because in the next slide you will see what problem it causes, that the lattice may go. And this is also that you have to take into account. So here you see different types of gallium nitride crystals, and you say, okay, they can be very nice. So they don't have all these growth issues. You see that if you want to enhance the diameter, sometimes it happens that a facet growth appears, then your crystal looks nice, faceted and hexagonal, but this is not what you want. The crystals are heavily strained and they break and so on. Then you have to measure, for example, over the whole wafer area of the whole crystal, you measure how the strain distribution is. In the ideal case, this is center symmetric, but this is not always ideal. So for crystal growth, you have to control the growth environment, or the growth condition, I would say, over a large area in a furnace, which is the size like this. You grow a crystal like this, but you have a furnace like this with gases flowing here. You have to control them atom by atom, so it can be very much uneven. So growth thickness can be uneven, then the crystal will be bowed and strained. This is what we monitor, for example, with Raman spectroscopy. So we apply Raman spectroscopy, and we make mappings over the cross sections of the crystal, over the whole crystal area, such that we know what properties the crystal has in terms of the atomic arrangement. And now if we come to the next boxes, which is processing of the wafers, it means that you also have steps before. So you have a crystal ingot now. And as we saw, it could be hexagonal, but no one wants to have an hexagonal wafer. Okay, so we have to trim the whole crystal body, which is kind of delicate because you do this mechanically. So imagine you order a material, a brittle material, atom by atom, and then you put brute mechanical force to it, and you grind it round. This is crazy. This is really crazy. It works. This is also done for silicon, big ingots, like 400 kilograms. This is really mechanically round trimmed. This is awful if you consider it from a crystal growth point of view, but it works. So first of all, you have to trim it round, and you have to saw it in slices, which is also big mechanical action. There are wire saws. They come like these egg cutters with many saws, so it goes through it very fast because it must be efficient. And then you end up and see what was frozen, I would say, into the crystal. Then you have a wafer with some properties. And this is what goes into epitaxy. So people doing epitaxy say, hey, tell me what properties your wafer has. But we know that, first of all, we have to watch properties of the crystal, because what is frozen in the crystal growth pops up with the AP wafer. So they can be bowed, they can be warped, they can have some odd shape. If it's not everything centrosymmetric, there can be crazy shapes of wafers, especially for the nitrides where the technology is not really utmost mature. So if you consider gallium nitride freestanding wafers, you see that there are many issues to these wafers, which is strong geometric bow or lattice bow, and you can have offcuts from the C direction. So this is just an example. It applies also to other materials, but the gallium nitride is the most prominent, I would say, example for these lattice bow issues. So you imagine you have a crystal body, this ingot, so the big crystal, and you have sketched the lattice planes, and they are bowed. And now you cut a wafer out of it, like this dotted box, in some direction, because for epitaxy, you normally want to have some, I would say, some certain offcut of the lattice to induce the step flow growth mode in epitaxy. So if you want step flow growth mode, you tilt your lattice towards the C direction a little bit. Of course, you want the 2-deck, so we will not flip it too much, but some certain offcut you need, such that the step flow growth mode in epitaxy that you want could be achieved. And this means that if you cut it in a certain direction, or even if you cut it with no offcut, with zero offcut, you will have steps at the surface. And these lattice planes emerge to the surface in a different, let's say, different inclination angle, and uneven over the whole wafer. So in the middle you have nearly no offcut, and at the sides you have big offcuts. This is all what you don't want in epitaxy, because the epitaxial condition responds to the surface of the wafer. And you see, for example, that if you measure such a wafer along the north-south direction, you have offcuts for one type of wafer. Of course, there are other suppliers, but this is one example, where you have offcuts between very close to 0 and 0.6 degree, which is quite a span, if you consider this from point of view of epitaxial conditions. And in the east to west direction, it's different. It's nearly no offcut. So it means that it's not even central. The wafer is like this. And this is all something which is not good for epitaxy later, and the quality of the epitaxy, we have heard, determines how good the device is. So there are also more than just the front side to be considered, which offers the offcut to the system, where the atoms come and form the atomic layers, but also the back side. If the wafer is bowed like this, it will not stick in your epi pocket. So all the temperature, let's say the temperature contact from the backside that you need to heat the wafer up very evenly, and also the position of the surface will vary if your wafer is bowed like this. And this is all what you don't need in epitaxy, because this will compromise the quality of the epitaxial layers. And if you monitor this in form of mappings, this is, to our opinion, the best way to do it, because it can be not only centrosymmetric, so just making crosses or star types measuring points is not good enough. You see, for example, here a 4-inch gallium nitride, also this exists. Then you see that you have radius of curvature, so this means the curvature of the lattice inside the wafer. It's also uneven. You have areas where the radius of curvature is very big in these red areas, and you have an area where it's not so big, but it's even close to the other way around. So you have something where the wafer can flip like this. You have wafers, they flip like this, or they go like that, which is all not what you want. And this is an example with aluminum nitride. So this is gallium nitride 4-inch. And you see, for aluminum nitride, it's a little better. So it's actually much better. The material is smaller, of course, but even if you have larger crystals like 2-inch, it's getting much, much better compared to gallium nitride. And you have offcuts which are on the order of 0.1 in the variation. Also the offcut direction counts, and you see even if you have large offcuts, they vary only between 0.1 and 0.3 maybe. So it's all not so severe in aluminum nitride like it's in gallium nitride, and this is also related to the growth method. So you don't have any chemical mediation here in aluminum nitride growth. It's more difficult balancing the gas flows, for example, in an HVPE process like this was done for that crystal. So it's much more difficult, and this is what I said at the beginning. The choice of the crystal growth process initially tells you how good you can achieve perfection in the crystal. If you have no other choices, of course, because your material is not growable as a crystal with another than this method that you have chosen, okay, then you're stuck with that. Then you have to make the best out of it. What you also see is that this varies quite a lot, such data like off-cut and off-cut direction and off-cut angles all over wafer. But if you see the spec sheets, if you watch them that are sent with a wafer, they are mostly giving median values or average values only, and you don't get such maps. And if you want to do epitaxy on such a wafer, okay, and then we have something, this concerns Sondre also very much in his PhD thesis. This is also true not only for native gallium nitride and aluminum nitride wafer, this is also true for gallium nitride on silicon, because of course you put this big epistack on it, and if you put this big epistack on it, the wafer gets bowed, because you have material with different matching in terms of structure and thermal match, and then the wafer gets bowed. And you see that this is a larger wafer, but the wafers must be controlled before the processing, because if a wafer is such bowed, you have maybe like 80 micrometer bow, or you have 100 micrometer bow. If you put an even thicker, the wafer either breaks, or you cannot put it to a processing anymore. So your wafer stepper will not take it. Or at least the person who's operating the wafer stepper will say, go away with this thing. So you cannot operate it as long as it doesn't stay flat. So let's come to the devices. Now it gets more complicated. If we think about how we now can transfer all this knowledge, we know the crystal must be perfect enough. We see that there are many parameters in the crystal growth that we have to obey, that we have to deal with. We have to deal with physics. This is the most important. So if you don't follow physical rules, this will punch you back for sure. You have to pay for it if you step over physics. So if the crystal is as perfect as we can do it, we have the issue with trimming the ingot, with sawing the wafers, preparation of the wafers, cleaning the wafers, we heard, is also an issue, which I will leave out here, because I would say this is a topic for itself, how to clean really a wafer, how to get rid of the stuff that is sitting on the surface and disturb. And let's deal about epitaxy, what that means. Now we're getting closer to the device. We have the crystal, we have the wafer, and now we have to put epitaxy. What does it mean? The ultimate goal for a semiconductor is the same than for crystal growth. The crystal layer, which is the big individuum, one crystal lattice, very thin but large, on the whole wafer surface, must be as perfect as possible and have no defects. How can we achieve this? We need perfect match of the materials. Then we have no defects. So we have a substrate of one kind, and we have an epi layer of the same kind. Then we have no defects. As long as this is whatever, not disturbed by anything at the interface, which is cleanliness of the interface, and so say it's not. But this is what we don't have in the gallium nitride on silicon case, for example. So we have a substrate of one kind and the epi layer of another kind. And now you have mismatch. Mismatch in two respects. So we have thermal mismatch. So if we cool something and heat something, which is the epitaxial process, so it has some temperature profile, then these materials will work against each other. So thermal expansion is different. And of course we have to adapt the lattices, because if you put atoms now on all of these atom balls, you put other atom balls, then they don't fit at the same places, so they are being displaced. And displacement in an atomic lattice means you form and create a dislocation. So the substrate must fit as perfect as possible. This would be the ideal case. Then you have no dislocations and you don't have problem with heating and cooling. And it has to match as good as possible in thermal respect. This is what we call homoepitaxy. This would require native substrate. The technology route would be gallium nitride on gallium nitride, aluminum nitride on aluminum nitride, silicon on silicon, gallium arsenide on gallium arsenide. But then you don't have devices, for example, like with polarization fields, where you put gallium nitride, aluminum gallium nitride of different kind, aluminum nitride on something. This would mean that you have to deal about doping if you do such devices. Classical silicon devices which have some doping. There you can do the homoepitaxy or silicon carbide homoepitaxy from the new materials. But this is not the case for the gallium nitride or for the aluminum nitride, but so far the substrates are not large enough. If the substrates would be large enough, we do gallium nitride or gallium nitride. And this is what we would want to have. But if you now have to adapt the epitaxial conditions, the epitaxy, as I said, reacts instantly on what it's offered from the surface. So the epitaxy means that you have an oriented layer in the same orientation, that the layer takes over the orientation of the substrate. And you have to create it by a step flow growth mode over the surface of the wafer. And if you have this, there can be many disturbances. And this is, for example, the off-cut angle. This determines the step flow. And this depicts the heteroepitaxy case and the homoepitaxy case. So you see, this is no off-cut also in this simple pictogram. And you say in homoepitaxy, we only take over things that come from the substrate. And in heteroepitaxy case, we create a lot of defects at the interface. Now what can happen if we do epitaxy? The lattices are being inclined a little bit. We create a step flow growth mode, and then there can be something that happens during the epitaxy of the substrate. So the substrate itself has some narrow specifications that you have to reach, and the common problem that we said is out of these narrow specifications. Now, this off-cut angle determines the step flow. Actually, it determines the width of the terraces and the height of the terraces. This is determined by the off-cut angle. This is what epitaxy will create in terms of terrace size. So how fast your step flow runs over the surface. And this is very delicate to the, let's say, to the gas flow and the temperature that you're applying during the epitaxial process. What you want to have is a bilayer step flow. And if you want to create this step flow, then you have a certain window for temperature and the gas flow of your media, like the TMGA, the TMAL, so the gases that you use to deposit the gallium nitride or the aluminum gallium nitride, and this creates the length of the terrace as a response to the surface offcut. So the problem is, if the surface offcut is uneven and you have a round wafer, then your epitaxy will be different in the middle and at the edges. So you have maybe something which is step bunching at the side. When you condition your epitaxial process more to the offcut of the middle of the wafer, and you say, okay, here epitaxy will be fine, you have bilayer growth, and here you have step bunching. And then you have a wafer where the devices or your function layers are put in the middle, but not at the edges. So the usable area of your wafer is anyway not large for a 2-inch wafer, and even smaller if you have only perfect epitaxy in the middle of the wafer. This is the consequence that comes out of this imperfect growth. So now we come again. How can we understand how the performance later of the device is? If we have now seen what all the problems from the materials is that come into play. And then we see again, we have only a sequence of epitaxial layers. So now we say the substrate wafer determines the quality of the epitaxial layer. The crystal determines the substrate quality, the substrate determines the epitaxial layer quality. And now the epitaxial layer quality determines the performance of the device. This is the way, step after step, the chain we have to go through. Now how we learn this. Now we say what is relevant for a device. So what defect is more relevant, what is less relevant. But understanding relevance means to say relevance is by definition. So if I consider something relevant, I always consider this towards a target, what I want to achieve. So If I look here, for example, this is an optical device, but it doesn't matter, can be any other. You have depicted the influence of the threading dislocations in the device on the output power of a LED at different wavelengths. And now you say, okay, we have something like 10 to the 10 dislocations in the epitaxial layer, and we find some power output of this LED for 260 nanometer wavelengths. It's fine. But we see that we have no power if we go to shorter wavelengths. If our target is to operate a device at a shorter wavelengths, this number of dislocations, or the total number of dislocations, matter a lot. If we say we are happy with 260 nanometer devices, then it's fine. Then we don't need to bother much. Then we say, okay, we make something like 10 to the 9 dislocations, which is very common. Then we are fine with this, and we have some decent output power, which is fine for LED. But this will never be a device able to emit 220. If we say, okay, we want a deep UV device and we have to emit 220 or smaller wavelengths, then we say any dislocations which is there counts. So we want to have no dislocation, really low, because any little dislocation will be deleterious. And then we say, okay, we need a most perfect crystal in order to get any output here in this direction. So relevance is a matter of definition. This is always what you have to keep in mind. And a good example here is what the quality of the substrate is determining. You see as an example here the sheet resistance in a HAMP device with an AlGaN channel, and the quality of the AlGaN channel here is expressed in terms of full width half max. So full width half max is smaller here, larger here, and you have these points where you say, okay, the sheet resistance we want to achieve would be in these regions, so it should be small, and the number of dislocations should be small. So if we have a better device here, like this rect triangle, it means that full width half max, so it's smaller, so structural quality is better, and we have the targeted sheet resistance. But this only functions if we put as a substrate an aluminum nitride substrate. For example, aluminum nitride substrate, underneath aluminum nitride layer, underneath the AlGaN channel, underneath the AlGaN barrier. If we put this all on sapphire, for example, then the number of dislocations is higher and the sheet resistance is far off what we want by orders of magnitude. So this is how the substrate determines it. But if you can live with it and say, okay, it's fine for what I want to achieve, then you don't need to bother further. Fundamental limits matter all the time. Only the fundamental limit, but everything else is also a matter of definition. So how come this into play? I think this was most of the transparencies were switched by accident. Okay, if we consider the properties of the, the properties of the substrate underneath, for example, a HEMP device, we want to achieve the bilayer step flow. I missed it, it should go before. Then we can have hillocks or step bunching. And you see, for example, here that how the epitaxial conditions, I would say, are influenced by the, other way spoken, how the properties of the terrace size, for example, so the size of the terrace determines your growth process, and how is what is the consequence if you want, for example, to incorporate dopants, or in this case here, if you want to grow an aluminum gallium nitride layer, which is an alloy composition, so at the same time you run two different reactive gases, so two tox gases, and this is, for example, with a silicon carbide device as an example showing that how the incorporation of dopant atoms also depend on the structural quality of the substrate here, because it determines the terrace size. So if you adapt your flow rates of the nitrogen and your donors for good epitaxial conditions, you see that the flow rate, which you have to adjust responding on the surface quality of your wafer, is determining the incorporation of your dopant atoms. And the same happens with the AlGaN barrier. over the varying offcuts and the varying terrace sizes during epitaxy, the system will respond with different aluminum gallium nitride compositions. So also the composition of your barrier for a HEMT device will vary all over the surface area, which is also not what you want. Sorry for having switched these two transparencies. Now we have to understand defects. Why are defects so problematic, and how differently can they be problematic, and what they are doing to the device? Let me know if you have any questions, if I go too fast and so, but we have only these 90 minutes, so keep your seatbelt fastened. The same is true here. A real crystal we have now. We don't have the perfect crystal, we have a real crystal, and it means that we have a deviation from the perfect periodic lattice. So it means we have atomic arrangement with imperfections, and it can be 3 types of imperfections, let's say, or 4 types. Let's put it in 4 categories. We have point defects, we have line defects, we have planar defects, and we have volume defects. And all of which you have seen for sure so far. So point defects are important or not important. They can be wanted or not wanted, depend on your target. Interstitials you don't want because you disturb your crystal. Vacancies you don't want normally, it disturbs your crystals. Impurity you don't want, but doping atoms, this is what you want. Doping atom is a point defect. It is something which makes a deviation from the periodic perfect arrangement in a crystal, but we want it. So doping atoms are fine point defects. Line defects, dislocations. We don't want them at all. There is no fine dislocation. We don't like it. Planar defects are surfaces. Surfaces is what we need. Because if we won't have surfaces, we don't have surface charges. Sometimes you want surface charges. You don't have interfaces putting functional layers on top of each other. So interfaces is something, surfaces is something we need. It's in fact a planar defect, a heterogeneous planar defect. Grain boundaries, we may want or not. Twins we don't want, stacking faults we don't want. They can all do odd things in a semiconductor crystal. Volume defects can be precipitates, voids, non-uniformity. A volume defect we also considered a strained region. Strained region is something we want to. So strained region we want, if we want to create a 2-deck, we want a strained region because otherwise we have no 2-deck. We have Seagate devices, for example. We want strained regions, otherwise it doesn't function. So some of the defects are wanted, some of them are not wanted, some are good, some are not good, and we have to look what we like and what we don't like. So let's go a little bit through what does a defect mean? Understanding a defect. It's like understanding the crystal. Understanding the epitaxy, let's understand shortly the defects. So what is the driving force to create a defect? I said a defect is something that is a displacement in the crystal, a deviation from the perfect atomic arrangement, and this is determined by energy. So the Gibbs free energy is one of the most fundamental properties we have on Earth, I would say, properties of solid matter, and it defines, let's say, the potential state of the crystal. So it says in what state the crystal likes to be. So everything on Earth follows a minimization principle, which is what the crystal as a matter also does. So it tends to minimize its free energy, its free Gibbs energy of the crystal, and this always depends on the defect content. So if you put defects in the periodic arrangement, you change the Gibbs free energy. And by definition, the perfect lattice needs some energy. So you put some defects like vacancies or interstitials, which creates a lower energy. So by this definition, there will always be some concentration of point defects in a crystal lattice. So the perfect lattice will consume them energy. So from this point of view, it lowers the energy to put some point defects to the crystal, which means that fundamentally there will be no crystal with no point defects. You can get as close as possible to remove them as much as possible, but no, it's essentially from an energetical point of view really hard to achieve. Then you put extended defects, and extended defects, they raise the free energy, the chip's free energy along this state. The larger they are, the more. And this is something that we have to consider in order to make things more perfect. And we see that these locations always store some energy. And this is how they behave. So this is to remind you what happens if we do epitaxy. We do heteroepitaxy now, heteroepitaxy case. So we gradually adapt the lattice. And because it consumes energy also, we have to make an energetical step forward to adapt two lattices that initially don't want to be together. So we have, it consumes energy and it creates defects. And we can mediate this by putting the buffer layers. This is actually what we do then from an energetic point of view in heteroepitaxy. And this creates that the energy is stored in the system, so it can be released by doing something, creating dislocations, bending. If you don't have plastic deformation in form of dislocations, then you have elastic deformation, and your wafer starts bowing. This is from the fundamental principle what happens, what the dislocations are doing, and the disturbances are doing, and the strain is doing. So you need a defect engineering and a strain management in order to get what you want. So how does it look? For example, how is the difference between the heteroepitaxy system and the homoepitaxy system that we have considered before? So here you see cathodoluminescence imaging. This is what we do as one characterization method. It works fine on semiconductors that are optically active. So we shine with an electron beam on the material and it emits light. And at such places where you have recombination of carriers, the material does not emit light. And then you can prove, which you have to do of course, like with the etching, that at places where dislocations are, you have no emission of light, so that these dark places are really places of dislocation. And then you can do correlative analysis with defect etching, and at such places you don't find emission of light. So you see, for example, here, cathodoluminescence imaging of a gallium nitride on silicon, which is 10 to the 9 dislocations per square centimeter, and you see that all these places are defects. So you have an uneven distribution. You have clusters, you have cell formation, you have places where you have no dislocations, you have alignments, for example. And here, in a native crystal, freestanding gallium nitride, you have 10 to the 5th dislocation or 10 to the 6th dislocation. Can be also 10 to the 4. If you have a monothermal material, you have 10 to the 4 dislocation, or even low. And then you see any of these points is a single dislocation. So you don't have clusters or alignments. And this is all fortunate for the device. This shows this is the physical way to go. Because material on material, gallium nitride on gallium nitride is happy, and it's not creating gallium nitride on silicon case, many dislocations with cluster uneven formation. It's getting more closer to the physics that we really want to obey, and where the devices should be the best. Understanding the defects, so a screw dislocation. Finally, we want to come to the point, why do dislocations act differently? So you have, for example, screw dislocations and you have edge dislocations. They are from their character atomically and energetically different. So if you have a screw dislocation, it means the lattice, or a lattice plane, a lattice point, goes around the lattice plane like this, inside the lattice. Whereas if you have an edge dislocation, you have your lattice, and it's like, imagine you put an extra layer in the middle of this, which is depicted here. It means that you consume space where there was nothing planned for in the lattice. So you create a strain field. This is what you do. You can characterize the dislocations by the geometry of the line vector and the so-called Burgers vector. The Burgers vector is the displacement vector. This is really where the lattice is displaced in let's say, in a measurable number. And the Burgers vector and the dislocation line are perpendicular to each other by definition for edge dislocation, and for a screw dislocation, line vector and Burgers vectors are parallel. It means that moving a screw dislocation inside a lattice needs more force and more action because it needs some climb effort compared to moving a dislocation, edge dislocation through a lattice. This is also something that can be different, and what you also see or what you can imagine is that a screw dislocation contains a lot of energy, so it stores a lot of energy. So you have a strain field around it, which is some huge displacement, and is monitored by a strong energetic content. So you have different, I would say most common dislocations in the nitrides lattices, in the wood-side type semiconductor crystals, which is threading edge dislocations, we call them TEDs, basal plane dislocations, and threading screw dislocations. The threading always means, it's a word which is not physical, it means that everything that goes along the C direction in the wood-side lattice and emerges to the surface, which is seen by epitaxy. It's not a real physical word. And this is also what we can see, these types of dislocations also we see in 3 types of sizes of edge pits if we etch the surface. Here you see how it looks, for example, in a cross-section TM image. And what you now have to see is that the dislocation cannot just stop in the layer or disappear because it stores energy. So it cannot just disappear in a crystal. So it's being built up in a crystal as a displacement energy, so you cannot just put it back to the place. This will not happen, so it has to do something. So if you want to get rid of dislocations, you have to do some action. And you see, for example, close to an interface, they can recombine, so of different Burgers type dislocations can annihilate, so then a negative and a positive Burgers vector direction annihilate, and you have on top of this no further dislocation. They can combine in bundles, they can form loops. Here you see, for example, that they combine in bundles. This one, if they stop here, it does not mean that they stop here in the lattice, they just disappear out of the TM foil, so you don't observe them anymore. And also this normally does not appear that they just start here for nothing and they disappear for nothing. It means that they are maybe laying like this, you only see this segment. So the dislocations have to do something to minimize their energy, and if you want to get rid of dislocations, then this requires some action that we have to do to them and to some energy that you apply to the system. Now let's come to the point defects. I said, okay, there are defects you want and you less want. So the crystal must be as perfect as possible. Extended defects are always unwanted because they deteriorate the performance. And point defects are something that are useful. And you see these, for example, in the emission of light. This is something we like. What they do, the dislocation, yeah, this also matters. We have different types of dislocation here. How they are lying towards the incoming current. So if you flow a current through a device, it matters whether your threading dislocation goes along the current direction flow or perpendicular to the flow. These matter more or less as well. So it's finally, if you consider the device, you have to question what is the geometry of the current flow towards the dislocations. How much time do we have? Half an hour. Okay. Okay, let's go faster. I'm sorry. Okay, I said everything follows the energy minimization principle. This is what you see here. It also telling you this transparency that we can also express in numbers. It's not only telling, but we can also express in numbers that a dislocation stores some energy. So it's not a free of energy place. So compared to the outside crystal, which is around the dislocation itself is a place of higher energy compared to outside. And the dislocation energy is proportional to the length of the dislocation. So as a consequence of the minimization principle, the dislocation always tend to be straight. This is what the threading dislocations are doing. Of course, there are also geometrical constraints. from crystallography reasons, but the dislocations won't go like this through the crystal, because this makes, from an energetic point of view, no sense. Which is good, because at least the dislocations want to be as short as possible. And edge dislocations always have larger energy than screw dislocations, and I will come back to this. This is what I said before. So you can combine dislocations. If you say, okay, now you consider the stored energy, the strain field around the dislocation, you say, okay, there is some compressive force. You see here H-type dislocation, some compressive strain, and some tensional strain. Both on the other side, so opposite of a dislocation. And this strain region, this is something that is active, even though if the displacement of the atoms in the core of the dislocation doesn't count. You have to keep in mind that there is a strain field around, and this strain material also is doing something. This stores the energy. Now we learned that dislocations can do something. They can form clusters, they can form bundles, they can go together, they can annihilate. And then you have point defects. And the point defects, which is your dopant, for example, or impurities, or if you have a gallium nitride with a carbon dope buffer, this is the carbon in the gallium nitride lattice, so it should be distributed evenly, as even as possible. And now imagine you put dislocations in this perfect arrangement with an evenly distributed carbon. And you have learned that a dislocation has a strain field which stores energy. So what happens? The dislocation can gather the point defects or the impurities. So they grab this extra carbon and they gather it around it. So inside the strain field, you can gather, for example, the impurities. So you have this strain field around the dislocation, and imagine over all these lattice around, you now distribute a dopant or an impurity. Then these start migrating to the strain field around the dislocation. And now imagine what happens. The dislocations can be decorated, so they are collecting atoms. Imagine what happens if you have metal atoms in silicon. This is a good example from solar cells, for example. So you had metal atoms as an impurity, and you have dislocations or grain boundaries in solar cells. And now, by energetic actions, these atoms go and decorate these dislocations with metal atoms. Then they get conductive. And this is what you don't want, because this is creating leakage current. So if you send now a current through your semiconductor material, it goes along where it finds the highest conduction path. And this is leakage. So this is what can happen with dislocation. They grab the point defects or impurities, get decorated. They can also grab dopants inside their strain field, not only at the core of the dislocations, but also in the strain field. And then something else happens. Not only that the atoms go to the dislocation and to the strain field, but also the vicinity, the neighborhood, gets depleted. So if you want to have your dopant evenly distributed, what you create is dot, 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 dot of cumulated dislocations and depleted neighborhood. This is not what you think is what you want for a device where you like even properties all over the world. And then imagine if you have dislocations that are uneven distributed, like we have seen before. So before, you see, the dislocations can be uneven distributed. And you have many, and imagine this big cluster collects more dopants. And then, oh, you don't have dopants here anymore. But if you have more distance, this is less severe. And you can see that this is true if you measure it. Okay, this is what I said. It's also grain boundaries you consider as an arrangement of edge dislocations. So this is the sign for an edge dislocations. So grain boundaries, in fact, you consider as a collection or lineup of edge dislocations. And this is an example for a solar cell, let's say, or grain boundary. And you say, sometimes you also want the gathering, because then these areas are free of impurities. So this is an example for impurity gathering also. But then the atoms, the foreign atoms, go to this place where you have stored high energy and where you say, okay, there are the dislocations. And this is what you can measure. We heard already the morning an EBIC measurement example. So electron beam induced current. We combine this with EDS measurement. So it's a measurement where you can have information about the chemical content at the same time, where you get information about recombination places. So what you do in EBIC, you measure places for electrical recombination. So you put a potential to your material and you divide the carriers, the holes and the electrons in electric field. Then you create excess carriers with the electron beam. And then inside your field, the excess carriers recombine or not. And they recombine, like with optical recombination, at places where you have dislocations. And this is what you see here. If you have an EBIC picture, for example here, of a solar cell, you see at any such places you have recombination of carriers. So if you run now a solar cell and say, okay, I want to have a current through this, or you shine light on it, say, I want to get the current out, or I want to get the electrical property of this material, then it's uneven. So these are all areas where you get no response. So this is the efficiency of the device, what you see finally. So this one is very good, and in such places you have no efficiency. And you can get this magnified and correlated place by place, and you see that these big dots, for example, then you go to the, this is scanning spreading resistance measurement. You also see that the current flow is higher here. Scanning spreading resistance is done at the atomic force microscope. So you put the tip of the AFM on top and you measure the current flow through the material. So you say, okay, now I have the EBIC picture, I see where the places of recombination are. Do they also create a current flow? And we say yes, because we measure the current flow as a current flow map. And we say, okay, this correlates with the dots that I see here. So any of such dots create a current flow through the material, so leakage, which I don't want. And if you then, by high resolution, create an EDS picture, you say, oh, at these places I find iron. So it means that in the crystal growth process, finally, where the solar cell material is being produced, there was a contamination of iron. This creates the precipitates, and this is compromising the performance of the device. Whether it's a solar cell or a transistor, doesn't matter. Okay. So the effect of a dislocation depends on different things. The orientation of the dislocation with respect to the current flow. So if you have dislocations vertical like this, current flow comes from here. It's a different case compared to the case where current flow goes along the dislocations. It depends on the original type of nature, whether it's a screw dislocations with a strongly stored energy compared to edge-type dislocation, and depends on the charge of the dislocation on the core structure. But any of these properties of the pure dislocations can be changed by segregation of atoms, for example, or depleting the surrounding. Why it is difficult for a device, such a dislocation? Because the dislocation creates niveaus in the band gap. And this is what we're talking about, recombination action. So a dislocation can be radiative, non-radiative, create, let's say, recombination channels over defect niveaus between the conduction band and the valence band. And this is the problem that we don't like. And here are some examples how we measured it in a device. Now when everything comes together, what we learned about growth, epitaxy, properties of substrate, properties of dislocations, now we put everything together and say, okay, how does it look in a device? And it's getting more complicated, but we can see quite a lot of things. Here you see a visual picture of the photoluminescence efficiency, for example, of a LED, and you see that there are places of non-radiative recombination at dislocations. So you see that, actually it's vice versa. So you see that there are places that shine, so it's illuminated. Actually, it's not that this is shining more than this one. It's color-coded in the wrong way. So these are the places of the dislocations, and you see it's not shining light evenly. So what you would like to have is an even blue layer where everything shines the same, and this is not the case because the photons being emitted are not evenly all over the device because the dislocations recombine the carriers. This is an example of local warming where you have a source and a drain contact here, you see, and later we have to look what is underneath this. This is what we do, so we see such type of pictures, we say, okay, this is a problematic area, and now we look directly inside what there is with all the knowledge that we have from crystal growth until defects on different scale. And here, for example, you see, but this is a lucky case, I would say, if you grab it in preparation like this, you see directly underneath a gate. In this example, there is a dislocation where you say, okay, this dislocation or dislocation bundle had caused the gate failure. This is a very direct evidence that you cannot achieve all the time. I will show you examples where you see that only by statistical means you can really achieve that. So dislocations that are directly under the contacts or directly in these very active areas like in the gate area, they always cause to the majority catastrophic failure of the device, whereas other dislocations can also cause gradually loss of performance. And this all is not so easy to be investigated. You can remember this. The problem that we have is we are looking on different scales, as I said at the beginning, and here it's depicted. You have dislocations on an atomic scale. You need a TEM or an AFM, looking on very small areas. Then you have the size of the structures, which is on the order of micrometers or millimeter or something. Then you have the size of the whole device. Then you have the size of the contact. So it's getting larger and larger. Then you have the size of the whole wafer with many devices. And you have the whole crystal, which gives you many wafers. So the scales get larger and larger. And to follow the whole chain from the beginning to the end, this means that you have to observe all the problems on different scales. I show you an example of depletion of dopants in the carbon dope buffer in a gallium nitride HAMD and what it's doing to the HAMD. So it was a gallium nitride on silicon HAMD, 10 to the 9 dislocations per centimeter. You see the panchromatic CL image. You see all these dislocations here. You see that there are clusters, that there can be arrangement of atoms and areas where there is nothing. You see the sequence. This is a step-graded a carbon step-doped sample. So you see that this has different carbon content. We did this for calibration purposes of the blue emission line. And we see that dislocations are visible as non-radiative recombination centers. You see all these lines are dislocations here. And we observed that there are local variations in contrast of the carbon dope buffer. This is the most important for what I want to show you. We can come back to this later. Okay. And then we produced, actually, Geoff Dalin made these samples from now Soitec, and before it was EPIGAN. He produced two samples, which were test structures or breakdown structures for HAMDs. And it was a set of two samples, which we called the failed ones and the good ones. So it means that the past ones, or the good ones, they were made for sustaining a higher breakdown voltage, so they lived until 850 volt, and the others failed below, which are the failed devices. The red ones you see from 400, from some between until 600, they failed. These were the basis where we investigated what are the critical defects. And I showed you that we can monitor the carbon content, and we observed the blue luminescence. And we observed the blue luminescence, and we observed we call it the near band edge luminescence. It's close to the band edge, and it contains a lot of, let's say, nivus in the band gap. And we saw that the blue luminescence, in this case, it's not always true, but in this case, it monitors the local differences in carbon content. And we proved this by Simpson that what we measured, the blue luminescence profile, is in nice agreement with the carbon SIMS profile. So we monitored the blue luminescence in such samples from a plain view image. And you see that there are areas which emit in blue light, in the blue luminescence, and which do not emit. So what you find from this, if you put all together, is that dislocations gather the carbon and deplete the region around the carbon. So what we found is that there are dislocations in such regions where we don't see the blue luminescence. So at the middle there is a dislocations, and it grabs the carbon. So you have region around the dislocation where the carbon is depleted. And this is the problem for the material and for the hem structure, because it means that if you have, like I said, an evenly distributed carbon content in the gallium nitride buffer that you want, you have a region with a dislocation or many dislocations where you have gathered the carbon, which comes from the neighborhood. So in the neighborhood it's not there. The material itself should be insulating with the carbon, but what you do, if you deplete the region by carbon, you make it more conductive. So the insulation is here, not all over the area, and you create something like an N-type region around a dislocation. So what you create is an envelope. Whereas you should have a semi-insulating material all over the device area, which you don't have. So this is what we found from this analysis. And if you have more dislocation, you can even deeper deplete it. Because in the middle between dislocation, you find that there's even less carbon. So it means now you can compare it with average distances of dislocations at certain dislocation density. You say, okay, interaction distance of a dislocation is so-and-so, where the strain fields overlap and grab even more carbon, and the size of such a carbon depleted zone has some size, and we can measure it. And now we say, okay, it can also happen that carbon depleted regions are overlapping. Then you have this very deeply depleted region. They are even more N-type conductive. And it's more harmful than if you have single dislocations which are isolated somewhere. And then a colleague in Aachen at that time, he's now at FBH, Hannes Jakob, in his PhD thesis made a calculation and said, I don't understand this dynamic trapping behavior of the transistor in a TCAD model. And he said, I cannot understand this. And then he tried to introduce, we call it deep carbon depleted zones, in the buffer and recalculate it, and then he could match his experimental results, which were the scarce, or his theoretical results by TCAD measurements. So at the end, it confirms that we have created, from analytical point of view, semi-empiric, I said, empiric model. And someone took it, which is very nice. So it's also very good if the experimental characterization people create something that it's being picked up and proved by the community. Just prove it, calculate it, say what you find. This is good. So the community should use these results and create whether it's good or not and what you can learn from it. And it could explain the dynamic trapping behavior if you introduce deeply carbon depleted zones in the TCAD mode, even a small number. And this was very encouraging for us to say, okay, the route that we have chosen is good, to look with this strategy that we have done. Then we went to AFM, and I had a very good PhD student who was doing it. And we said, okay, with the AFM we can measure very directly. Now we have learned what the dislocations may do. Now we go to a hand structure, we say there is a 2-deck, and we measure with the AFM tip in a vertical geometry, and we let the current flow between the tip and the backside. And what we see, we make tapping AFM, we see this depression at the surface, we see just a surface profile, we identify dislocations at certain places, and now we run the current through it, observe the same place, but what we image then is current flow paths. So let's say locations where we have prominent current flow, higher than the background, and these are such places. And then we started correlating it with the places of dislocations. Where you see here, we have these, we call it leakage spots, the big red ones, and we observe whether there is a dislocation or not, or many dislocations, and what they do, and we try to identify the nature of such leakage, such dislocations or such defects that are underneath such leakage spots. This correlation scheme is quite complicated because now you have to put everything together. Before processing, after processing of a device, observing the epitaxial layers, observing the whole epitaxial stack, observing the substrate. Now put everything together with all microscopic means that you can achieve and say, okay, they make sense. Luminescence imaging, conductive AFM, tapping AFM, and of course we observe the material plainly in SEM. Now you get this picture and you can overlay it. Luminescence shows us the dark spots at any place where there are dislocations. These black ones. We put the blue points. And we can also distinguish between the types of dislocations. Threading dislocations, threading through dislocations, edge dislocations, mixed types. Then we say, okay, we have high current, low current flow. And we put everything together and on top of each other. We say, okay, those are areas with large leakage where we find nothing in structure. We don't know really what this is. So this is unclear. This may be a technological issue, not coming from the material. But otherwise, we can make one-to-one correlation. But imagine that this is on a micrometer or nanometer scale. So whatever you characterize at SEM in a larger sample, you have to find back the place of AFM under a micrometer scale. And you don't have a microscope like it is at the SEM. But it's something really great what you can do, because we also understood what the nucleation layer is now doing. We have another 2 sets of samples, breakdown voltage 450, breakdown voltage 500, very broad large distance. Now we observe the same AFM, we put a current through this, make a current flow map, and we say, oh, there are so many leakage spots. There are only few leakage spots. Oh, this must be the material with early breakdown. But it's not. This is the material which is here. And this material with many leakage spots is a 1200 volt material. So how come this? So you always have surprises. So what is the influence of the nucleation layer in this case? Why it determines early breakdown? And what we found is, now we go to cross-section analysis. And we see the interfaces. And we have V-pits. But are the V-pits relevant or not? We said by definition. Are there many V-pits? Do we need the V-pits? Can we be angry about the V-pits? We don't like them. Because the V-pits, and I can show you, they collect impurities. And this is what we don't want. V-pits are relatively large, much larger than a dislocation. And if you observe them all here, they collect dislocation, they collect impurities, and they collect dopants. Because of crystallographic reasons, they grow with inclined sidewalls, which are atomically stepped, not flat like a C-plane. So incorporation probability of an atom at stepped sidewalls is much higher. So it's attraction of impurities to go to such V-pit sidewalls. Now we observe the near-band edge emission and the blue emission, which is sensitive to the carbon, and we say, okay, this is carbon and oxygen. We later identified it by microsims. We said, okay, this is carbon and oxygen that's going to these V-pits, and carbon and oxygen, if the oxygen goes there, you have an N-type dopant. So they are N-type conductive. So this is what creates leakage. So plainly spoken, the V-pits have a higher impurity content. They have less carbon, as you can see here, and they have a high content of oxygen, so they are highly conductive gallium nitride. And this is what is causing the leakage. And this is Why the sample with the 1200 volt, it has less leakage spots because it has less VPITs, not because it has less dislocations. So don't be cheated. And we can see this if we count the number of VPIT dislocations underneath the area of the device. And then you need something extra, which I haven't talked about. You need clever sample preparation. Because samples with the layers in the cross-section have very thin layers, so how can you observe it? We geometrically widen the structure. Geometrically widen means you cut with an inclination through it. You create a wedge-type sample. And then you see then you can observe the VPITs over the height of the sample, which means over the height of the layer stack. You do the same experiment and you find back the leakage spots at the places that you can correlate to the VPITs. And then you make the plots. Then you calculate what you see from all your pictures, which means that you calculate or that you count the number of VPITs underneath the device. And then you find the number of VPITs underneath the device correlates with the good and the bad samples. And then you say, now I know that underneath these samples we have more VPITs than on the other one. There's total dislocation density is the same. This is how you do it. So here you have VPIT density as it is counted, and here you correlate it to the breakdown voltage. Time is finished, I heard. Time is finished, I heard. So I leave the decision to you. I have 5 more slides to go. Do you want to hear it or not?
Yes.
I love you. Okay. We have a complicated correlation scheme, and I said it's all about making a clever test device. Because now we go to the devices, and we say, if you have a device, everything is covered by metal. This is crap for someone who wants to analyze. It's good for the device, we need it, but we cannot shine through this metal. Not with a simple electron beam and the gentle excitation conditions we need. We cannot touch it with the AFM tip. So what we do, we create a sample which we observe in S-grown, and then we say, okay, we do everything until the ohmic level and so on. And then we locally etch the silicon nitride away, and we have an open area. And after all these, of the temperature budget and processing, we observe what I described before, locally at such places. SEMCL, also we do the AFM picture, and then we go further with the Schottky level processing, and we say, okay, now we have microdiodes. And this is a crazy nice experiment. We make microdiodes, and at such places, in these open places, we observe everything that we have observed before, and we have full correlation from the final device to the material before. I maybe consume most of the time that's running around. So I'm sorry. Now we measure what is underneath such little devices. So we say, okay, we now calculate it, and this was done by the electron beam deposition for this first example, and Farid did it actually. And it was not so easy. He was not happy because it's so many contacts, very small, and he has to deposit with E-beam. And now we see, okay, at such green places, that will be later the device. And we have characterized the area before, and now we see, okay, what is going to be underneath this little device, and so we superimpose everything that we have measured, and we can make the direct correlation. And keep in mind that we always have to find this back on a microscopic scale, which is not so easy. And here you see now the CL image, and we see the little contacts here. And for example, I have marked this. We now scan them all and look at it and say, okay, we have one dislocation, we have many dislocations, we can identify them spreading through dislocations 2 times, and a mixed type dislocation. We have something where we have no, and we have large leakage area. And all these little diodes we measure now with IV curves. It's a whole lot of work, but it's a crazy good result, which we really liked. And we get these many IV curves. Then there is a lot of modulation involved, because we modulate it as a 2 diodes model. And we say, okay, now we plot something that we call is P. This is the function, this is, let's say, the area fraction of conductive dislocations underneath the diode area. And we plot this against the breakdown voltage, and we see, okay, that we now can classify this. And finally, if we make the model for this, we can associate the gate failure to the number of conductive threading dislocations at the edge gate, at the gate edge. And this reveals clearly that the total number of conductive dislocations, which is located close to the edge, is in that case determining the early breakdown of the device. And this was the first time that we were successful really showing the full chain from the material at the very beginning until the final device, and we directly could correlate it to the performance of the device. So this is the consequence, how it should be, how a better gallium nitride should look. I think this red frame says everything. And how would it look? You can see it here. This is an example for vertical gallium nitride power switching transistor. And they are particularly sensitive to the type and quality of the gallium nitride substrate. And you see that they are, for example, first of all, they are much better than the ones compared to gallium nitride on silicon, and also they are vertical. And you see that there are 3 types of material, 2 HVPE gallium nitride growth material, and the monoturbo material. A monoturbo material has 10 to the 4 dislocations, whereas HVPE gallium nitride typically have something like 10 to the 6 dislocations per square centimeter. And you can see that this performs, I would say, much better in many respects. And there you can see that it's sensitive to the total number of dislocation. And before you saw that it can be sensitive to another dominating defect, like the V-pits. And before you also see that it's a matter of what is the nature of the dislocations and the surrounding, if you have the gathering effect with the carbon. And that is, I thank you that you wanted to see the last 5 transparencies, because it told me that I was not all over boring you. So I thank you for the intention, for your attention. And it's all about understanding and creating future technologies. Thank you very much. Those are the people who did that.
So thank you for the extensive presentation. Now we have time for a few more questions. Anyone? Yeah, I think so. Okay. So
you're welcome to ask anytime.
There's one, yeah.
Thank you for your interesting talk about defects. Actually, something very interesting me is the V-pits. You introduced that this might be a source for the current leakage. Actually, in my growth, I also observed a very typical V-pits, but I don't know what's the region. You said this appears in the nucleation layer, and it's also in my nucleation layer. And could you please explain what might be the reason for the generation of the V-pits?
I think it depends on the quality of the nucleation layer. So the nucleation layer has several parameters that you have to define whether the nucleation layer is good or not. So it's the thickness of the nucleated islands, it's the number of the islands, it's the shape of the island, it's the density of the island. And if you say, okay, you now have to find an optimum between, let's say, the number of nucleated islands per unit area and the height and the side walls, and which creates density. And you have to target a certain density of these nucleation islands in order to enable the next layer to close and coalesce this 3D shape to a 2D shape. Because later you go from a 3D nucleation, that is what you're doing in these in these little islands nucleation, in the nucleation layer, and then you want to achieve a layer by layer 2D growth. And there is a transition which is a function of all the parameters that I said, including the temperature regime where you grow the nucleation.
Okay, thank you.
And these need to be optimized.
If this is a source of the quality when where the islands are merging together, is it detectable, for example, by XRD, for example, rocking curve, or because it's when this is the merging of the islands, it might be the source of dislocation. Can we detect the dislocation to determine whether there's or not? Because in the further layers we can see it if further GaN layer, GaN layer, for example, are grown.
The further layers will react on what you're doing in the nucleation layer, yes. So you have to characterize the nucleation layer very roughly. This could be by XRD measurements, but I prefer also other measurements, because the XRD measurements, you have some models that you have to apply to explain what is the dislocation content, and the models may not fit, because you have special type of dislocations that are not included in the model, which consider statistical distribution of dislocation types, which is not true. And then you can observe microscopically, maybe the density per unit area of your nucleation islands, the shape of the nucleation islands, and the size, or the height, and then the quality of the next layer. And monitor the quality of the next layer. Then change, monitor the quality of the next layer.
Okay, thank you so much.
So, are there more questions?
Do you think that these impurities play a role when we have this VPIT formation?
That the impurities play a role in the VPIT formation. Yeah, they can play a... Actually, you cannot really distinguish between... The VPIT formation is something that is also for geometrical reason coming from the nucleation layer. But on the other hand, you have to nucleate the sidewalls. And nucleating the sidewalls is a question of supersaturation at the tip of the VPIT. So if you have, even if you have a dislocation, which creates you, let's say, a spiral source or something, you have to nucleate and give some energy to the nucleation of the sidewalls, which are less preferable compared to the C-plane. So you have to give some extra energy which nucleates this VPIT. And this is something that you can achieve by collecting impurities at such places. This will higher the supersaturation, and in this sense gives an energetic, favorable formation for the sidewall, for the inclined sidewall. Yes. Actually, we have there is a paper from a former student of mine, Michael Knetzger. He has calculated surface energy because of these VPITs. Because the question was also why the gallium nitride forms a VPIT with the Clyde sidewalls and not the hexagonal prism. So it's a geometrical consideration which comes to the point that there is this nucleation energy with a supersaturation needed to nucleate the sidewalls. But you cannot really distinguish if you have both in once and you find the impurities inside the VPIT. You cannot say what is chicken and what is egg. Yeah.
Okay, any more questions? No, so let's thank again the speaker.